How's everyone doing? This is Dr. AJ Kumar, PhD. We're reading section 1.2 of Readin, which is called, or correction of Artin. This is called row reduction. So Artin's book is on abstract algebra. Let's just take a brief look at the table of contents actually before we get into this. Scroll all the way up. You should buy this book. There will be a link to buy it. Link to Amazon down in the description. I don't. Whatever. I just links to somewhere you can buy it. Maybe don't use Amazon. Uh, so, abstract algebra, it's the language of pure mathematics. Chapter 1 is just matrices. And Arden's point of view is that matrices are sort of the fundamental, most important thing in abstract algebra, and that's a correct point of view. Um, anyway, so chapter 1 is matrices. We went over the basic operations, so adding, multiplying matrices. Row reduction is the process through which you can either solve a system of linear equations, which is equivalent to finding the inverse equation of a matrix, and we'll get into that. The matrix transpose, determinants, permutations, other formulas. Chapter 2 is groups, so the three fundamental topics in abstract algebra are groups, rings, and fields. So all about just basic stuff about groups. Vector spaces, that's more linear algebra, so linear algebra, it's a study of linear operators on finite dimensional vector spaces, and the idea is that every matrix is a linear operator and every linear operator is a matrix, and there's a one-to-one correspondence. So given a linear operator, there's a unique matrix that corresponds to it, and given a matrix that's a linear operator, it's fairly easy to prove that a matrix is a linear operator. It's a little bit more challenging, but not that hard, to prove that every linear operator is itself a matrix, and all you have to do, you can actually just construct the matrix by tracking where each basis vector goes, and he'll get into that. Linear operators, that's more linear algebra. Applications of linear operators, more linear algebra. Symmetry, I guess this is sort of abstract, kind of applied group theory, maybe. More group theory. Here's sort of the core basics of group theory. Bilinear forms, so another word for the bilinear form is the dot product. That's chapter 8. Chapter 9 is linear groups, so this is both group theory and linear algebra, which is called representation theory. Then group representation, so that's representation theory. Rings, this is the second fundamental topic in algebra. Factoring, so this is sort of the core of abstract number theory here. Abstract arithmetic maybe would be a way to think about this. Linear algebra in a ring, so this is sort of generalizing linear algebra instead of being, abstract linear algebra. Fields, this is chapter 15. This is where we're getting into, alright, we're about to dive into abstract algebra, crazy town. Is finite fields, the theory of fields, so groups, rings, fields. Chapter 15 is fields, which is the third basic topic. Galois theory, this is sort of maybe a capstone of a basic abstract algebra course. Obviously, it's the last chapter. But the capstone of a basic abstract algebra course is fields, and this is where you get into, okay, now we can start really digging seriously into the really interesting parts of abstract algebra. You have to understand Galois theory. And I think group theory really actually starts with Galois theory, but to sort of appreciate it from a modern point of view, you actually end with Galois theory, which is kind of an interesting historical note. Anyway, let's get to section 1.2 and just start reading. Okay, 1.2 row reduction. Left multiplication by an n by n matrix A on n by p matrices, say ax equals y, can be computed by operating on the rows of x. If we let x sub I and y sub I denote the ith rows of x and y respectively, then in vector notation y sub I equals a sub I 1 xi up to plus a sub 1 n xn. Now, the problem, this is correct, and I've tried to, you can convince yourself at this point by writing it out, and maybe I'll try to do that, but I haven't been able to find I actually have kind of soured on the idea of matrices, because they're these very basic and fundamental facts about them that aren't that sort of emerge from the definitions but aren't obvious in a sense. So this is true, and let me just maybe give you a quick little example to try to illustrate why this is true. But I can't. It's so much effort to try to make this obvious. I can't quite figure out how to make it obvious. So let me just try. Let me get the drawing pad here, and I'm just going to try. Okay, and so instead of the subscript notation, I'm going to use a more Lispy note. I'm going to use a mixture of kind of Lispy notation. And I'm just going to give an example, maybe with 1 row, and maybe we'll do 2 rows. So here's the matrix A. A, 1, 1. Okay, so instead of the subscript notation, I'm just writing it using these parentheses, which is called an S expression. Look that up. A, 1, 2, and A, 1, 3. Okay. Times, and I'm going to write the matrix X here. X, 1, 2, friends. I wrote it down on paper. Oh, nope, that's X1, 1. I want X1, 1, parens, X1, 2, X2, 1, X3, 1, that looks like 7, 1, X2, 2, X3, 2. Is that correct? Looks like it. And let me zoom out a little bit. So again, I just don't love this notation. But maybe the way to think about this is you imagine rotating this row here and multiplying by this column and then adding. And so this is equal to, so big matrix, and we're going to take a sum times A, 1, 1. So I'm copying this matrix here, and I'm going to do it vertically. A, 1, 2, and A, 1, 3. Times this column. So I'm going to copy the column. X1, 1, that's too close together. X1, 1. X2, 1. And notice here that the second index of A's matches the first index of the X. 3, 1. Okay, and then we're actually multiplying component-wise each A1 by, so this gets multiplied with this gets multiplied with this gets multiplied with this, and then you take the sum. Okay, and that is just the first component in this row vector. And then the second row vector, you do the same thing but with the second column of X. So plus times A, 1, 1. And we're just going to copy the same A's. A, 1, 2, A, 1, 3. And then, but now we're doing the second column of X, so X, 1, 2. I'm trying to give you some visual intuition here. X2, 2, X3, 2. Okay. And then in each of these components, we're going to be taking a product of A12 and X22. And then finally the sum over all of these products. You see this the amount that you have to write grows very big. But the basic premise is like flipping this A on its side and then taking the product of each, this A with this X, this A with this X, this A with this X, taking the sum and sort of collapsing vertically using the summation, doing the same thing over here, collapsing vertically using the summation. And then if we have another row of A, then we would get another row down here in this matrix. That's exactly the same pattern. And so there's a lot going on here, and it's very confusing. It's so fundamental, but it's so hard to write, or it's so hard to visualize. And you just have to kind of play with it enough and convince yourself that this is true. And I at some point, maybe I'll think of a good way to sort of visually represent this. But at the end, you either have to just accept that this is correct. Oh, and let me just show you, which is that let's group by the A terms here. So this is I want to show. So this is plus times A1, 1 times the vector. Well, we look at where does the A11 occur. It occurs in this vector. So x1, 1, x1, 2, and then close the times. Let's do another times. Well, let's look at where A12 occurs. A12, and then we have another vector, x2. I'm just rewriting the above thing, so this is equal to the above thing. So this is x2, 1, x 2, 2. I'm getting carpal tunnel in my hand. Let me stretch my hand out. Let me make sure I'm recording on the correct microphone. I am. Looks like it. Then, of course, you guessed it, times A13 times the vector. Well, let's just copy the pattern. x3, 1, x3, 2. Okay. And then let's close the times and close the plus. And so we're really doing, you can visualize this row, rotating it and becoming a column, dotting it with each of these columns, and then collapsing using the sum. Forgot to close a parenthesis there. Maybe let me try to draw that. So A1, 1, A1, 2, A1, 3 times, let me just write out the matrix. X, 1, 1, X, 1, 2, X, 2, 1, X, 3, 1, X, 2, 2, X, 3, 2. What I want you to visualize is rotating this by 90 degrees. So now we have let me go a little bit lower. So we have A1, 1, A1, 2, A1, 3, and I'm just going to copy the matrix again. There's so much writing going on, and it's linear algebra is elegant, but it's not elegant in a nice way. Those look like 7s. Let me. Then this is x1, 2, x2, 2, x3, 2. Okay. And I want you to visualize pushing this into here and then collapsing using the sum. So then we get, that's maybe not going to be big enough. Let me just plus, we're collapsing using a sum, times, and I'm just rewriting what I wrote above, a1, 1, x1, 1, close the times, got another times here, stretch my hand out, a1, 2, x2, 1, times a1, 3, x3, 1. Stretch my hand out, shake it. Hand's cramping up. Okay, and I'm, yeah, I guess I'll write it. I'm at 33% zoom. Okay. Plus times a1, 1. So we can copy the a's. A 1, 2. A1, 3. And then we're going to copy, so we copied this column here, we're going to copy this column down here. So x1, 2, x2, 2, x3, 2. Close the times on each of them, and then finally close the plus. And then finally, this is the row. And then if there's another row, you do this again. So you see there's a lot of moving parts here, and I don't like moving parts. But unfortunately, linear algebra is very, very elegant. And there isn't just an easy way to see this. It just is. So maybe I'll figure out a better way to visualize this at some point. But this is what he's saying. This whole thing is what he's saying with hands cramping up. It's this muscle between my wrist and the base of my thumb. And maybe it's because this drawing pad I have is just comically small. Maybe I should get a bigger drawing pad. Anyway, so it's a linear combination of row vectors. But all that's happening here is what I'm describing here. And I just don't know an easy way to say it. And so he's showing an instance. So for instance, the bottom row of the product. So we take the, let me switch to Control-Z. Sorry, I used two different programs and they have two different sets of keyboard shortcuts. For instance, the bottom row of this product. So maybe let's let's try to visualize it. -2, 3. Got to give myself enough room. Control-Z. And I want a small pointer. Plus -2 times 1, 2, 1, 3 times 1, 3, 0. And so this is going to equal plus of, what is this going to be? -2, 4, minus 4, minus 4, minus 2. I'm going to just draw over 3, 6. No, that's 9. 9, 0. And that will be, you just add component-wise, so that'll be 1, 5, and minus 2, which indeed you see is the bottom row here. If we did the same trick with the top row, we would get the top row. And there just isn't an easy... Oh, that's an eraser, apparently. That keyboard shortcuts are different in the two different programs. Okay. And I guess it's true, and there isn't an easy way to say it, unfortunately. Or it isn't an easy way to see it, unfortunately. Okay, left multiplication by an invertible matrix is called a row operation. Maybe if you watch, can't remember his name, the channel is called Math the Beautiful, and he has a great linear algebra playlist. I highly recommend that. I talked in another video, which I'm not sure if I've published yet, about Gilbert string. And this Russian guy, Pavel, I can't remember his last name, Pavel something, he wrote a book called Tensor Calculus and the Geometry of Moving Surfaces. So, or something like that. Calculus of Moving Surfaces, something like that. The channel is called Math the Beautiful. I think he was Gilbert String's graduate student. And so he has Gilbert String is sort of the king of linear algebra. His linear algebra playlists are good. But Pavel, can't remember his last name, Grinfeld, something like that. He's a Russian guy. Has a great linear algebra playlist, and he really explains intuitively, and I can't remember his explanation, but multiplying by the left operates on the rows, and multiplying by the right operates on the columns. That's the correct way to think about it. So left multiplication by an invertible matrix is called a row operation. So if you really want to understand that, go watch Pavel Grinfeld's linear algebra playlist. And I'll try to remember to link it down in the description. We discuss these row operations next. Look up Math the Beautiful linear algebra playlist. Wonderful playlist. I highly recommend it. Some square matrices called elementary matrices are used. There are 3 types of elementary 2x2 matrices. Type 1 is, or type I, I'm going to use type 1, is 1A0I or 10A1. Type 2 is, so type A is where you're going to add one row to another. Type 2 is transposing 2 rows. Type 3 is multiplying one of the rows by a constant. There are also 3 types of elementary n by n matrices. They are obtained by splicing the elementary 2x2 matrices symmetrically into an identity matrix. They are shown below with a 5x5 matrix to save space, but the size is supposed to be arbitrary. So you put an A somewhere. A should not be equal to 0. Somewhere on the off diagonal. So one non-zero off diagonal entry is added to the identity matrix. This represents a transposition of 2 rows, so all it does is take one row and swap it with another row. The ith and jth diagonal entries of the identity matrix are replaced by 0, and 1s are added in the ij and ji positions. Okay, and this one is just taking one of the diagonal entries and replacing it with some number c, which is not equal to 0. And it says one diagonal entry of the identity matrix is replaced by a non-zero scalar c. The elementary okay, this is what I was saying. The elementary matrices E operate on a matrix X in this way. To get the matrix EX, you must, with type 1, with A in the ij position, so this is the one that's adding multiple of one row to another. So this is like if you have a system of equations, we're adding 3 times the first equation to the second equation, something like that. With A in the ij position, add A times row j of x to row I of x. So It's taking if you imagine it as a system of linear equations, you're taking a linear equation. So let's say it's 3x plus 2y equals 7, and I'm just going to say x plus y is equal to 2. If we add 2 times, or we add let's say minus 3 times the second equation to the first, that corresponds to this matrix. It'd be 1, I think it'd be 1 minus 3. Fact check me on this. That's your homework. That's your exercise. Times 3, 2, 1, 1. And if we add 3 times the second equation to the first, that should be equal to, minus 3 times the second equation to the first. We should get 0. 2 minus 3 would be minus 1. And then the second row would remain unchanged. And then if we do the same thing, so add minus 3 times 2 to 7, that should be equal to 1. So minus 3 times 2 is minus 6. Add that to 7 and 2. Let's actually just check this live. So let me try to zoom this in. Okay, let's call this first matrix A is equal to 3, 2, 1, 1. Okay. E is equal to NP matrix 1 minus 3, 0, 1. Okay. And then let's just check A. That's correct. E, that looks correct. Let's try E times A. Yay, I did it correctly. And then let's call B equal to NP dot matrix 7, 2. Okay, and then E times B. Yay, I got it right. Okay. That's the idea. Okay, in type 2, that's interchanging 2 of the rows, so that's just transposing 2 of the rows. If you have a system of linear equations and you just change the order of the equations, it doesn't change the system of linear equations. It doesn't change what the solutions are. The order doesn't matter. And then type 3 is just multiplying one of the linear equations by a constant. That again does not change the linear equation. Anyway, okay. I'm not going to verify those because those are much simpler. This one is the one, type 1, this is the one that's hardest to see. I should not use my mouse for this. Let me use the drawing pad. This is the one that's hard to see, and I think I just demonstrated it reasonably well. You know what? That's annoying because the trackpad, so normally there's a button on this pen, and in the painting program, if I press the button on the pen and then move the pointer, it moves me geographically. And if I do that in the PDF editor program, it turns on the eraser, and that's annoying. There's another button on the pen. Let's see what that does. Nope, that also, both of them, I think, yeah, both of them turn on the eraser. That's really annoying. I wonder if there's a way to change that. Anyway, these are called the elementary row operations. Okay, the elementary matrices are invertible, and their inverses are also elementary matrices. By the way, a great way to prove that something is invertible is to find its inverse, and that's what he's doing. So the inverse of an elementary matrix is the matrix corresponding to the inverse row operation. So do the exact same, it's Control Z. That's what the inverse is Control Z. So subtract row J from row I. Interchange, so in particular, the interesting one is that if you do a transposition and you do the transposition again, nothing happens. So the inverse to this, so the inverse to a matrix, an inverse to a type 1 matrix. So let's say this is 1, 1, 1, 1, and then you have some A. You take the transpose of this, and then you still get the 1s on the diagonal, but then you also multiply the A by minus 1, A, and I think that's what the inverse is. So actually, you know what, we can check. Let's go up here. So we had A, and we had E, and I'm going to try, let's call this F is equal to np.matrix 1, 0, 3, 1. Okay. So let's look at A again. E times A, and let's try F times E times A, and that, uh-oh, I made a mistake. Let's get A. Uh-oh, what's going on? My keyboard is spazzing out. A, F. Let's try E times F. That should be, it's not the identity matrix, so let's look at F again. Oh boy. This is why you shouldn't do live demos. Let's actually see, what does it say the Let's try np.linalg inv. Okay, so actually, instead I should put the 3 up here. I was mistaken. See, this is why I don't, it's just, it relies on doing this juggling in your head. So let's do F times E. Okay. So F times E times A, obviously that'll give us back A again. Okay. All right. The diagonal matrix with C, where C is not equal to 0 on one of the diagonal, that just multiplies one of the rows. And if you multiply on the right, it'll multiply one of the columns. The transposition, obviously you do a transposition twice, you get the inverse, so that's why it says again here. And then by C inverse, this means 1 over C. So the if you have 1, 1, C, let's just say the inverse of this is equal to 1, 1, 1 over C. Yeah, it's the same. Should use the same type of brackets on both sides. Anyway, you get the idea. Okay, we now perform elementary row operations 1.2.5 on a matrix M with the aim of ending up with a simpler matrix. Okay, so this is very vague at first, but what he's going to get to is row-reduced echelon form. And, sorry, I got a light on, it's distracting. Let me try turning. Is it too dark? Let's try turning on the light to low. Okay, that's not bad. Anyway, since each elementary operation is obtained by multiplying by an elementary matrix, right, so we can express the result of a sequence of such elementary operations as a multiplication by a sequence E1 up to EK of elementary matrices. So you do one of these row operations where you try to make the matrix simpler, and so you do the first row operation, that's E1 times M. You do the second row operation, that's E2 times, well, the previous simplification. You keep doing that until you get the matrix into the simplest possible form, which is called row-reduced echelon form, and he's going to talk about that in a minute. Now, what the purpose of the simplification ultimately is that maybe a way to say it is you simplify a system of equations until the system of equations has an obvious trivial solution. I don't want to say obvious and trivial, but until the solution is straightforward, then you can solve that. And then, let's just read what Artin has to say. As an example, we use the elementary operations to simplify a matrix by clearing out as many entries as possible, working from the left. All right, so here he did two operations. See the double arrow? So he subtracted. So this would probably be, this double arrow probably equals 1. Oh no, it's a 3. It would be a 3 by 3 matrix. So let's do 1, 1. Nope. So the first operation he did, let's write that over here. 1 minus 1. You know what? I'm not going to try to do it. I'm gonna give you my guess, but I'm not guaranteeing that this is the correct answer. So fact check me. This is the first one. So subtract. Take this first equation. Subtract the first equation from the second equation. So second equation minus the first equation. And then first equation minus the third equation. Or third equation minus the first equation. I think that's the operation that transforms this into this. Again, fact check me. Use NumPy. And he's, let's see, what... Anyway, so imagine if this is a system of linear equations. You're just simplifying the system of linear equations by you isolate the first variable on its own. Okay, second variable. Okay, now from here to here is a transposition. So all I did was transpose these two rows, which is one of the elementary operations. So instead of 0, 0, 5, 5, 1, 0, 1, 3, 1, 2, we now have 0, 1, 3, 2, 0, 0, 5, 5. And the important idea is identifying a pivot, which is what the blue lines circle. So the first one, you identify this as the pivot. The second one, you say, this is the pivot column, but it should be, should move the pivot up here. Here's the pivot. We need to eliminate above. That's what this blue arrow is. So take this second equation and use it to simplify the first equation. So this matrix here maybe is, there's two arrows. What are the two operations? Eliminating above and eliminating below. What is... Ooh. There's something I'm not seeing. Anyway, eliminate above, and then multiply this bottom equation by 1/5. That's what the two operations are. Then use this pivot down here to eliminate above. And then this matrix is called in row reduced echelon form. I don't know why it's called echelon form, but that's what it is. And the bold face are what's called the pivots. Let me write that down, pivots. Anyway, and he's being vague about what he means by simplified. So he says the matrix M prime cannot be simplified further by row operations. And he's being vague and nebulous about what he means by simplified, but he will define it in a little minute. Here is the way that row reduction is used to solve systems of linear equations. I need to drink some water. Suppose we are given a system of m equations and n unknowns. So that would be an m times n matrix. Mike times November matrix. Say ax equals b, so x would be a column vector. So where a is an m by n matrix, b is a given column vector, and x is an unknown column vector. So a and b are given. to solve this system, oh my god, he's doing this augmented matrix. I forgot about this. Augmented matrix. This is the stupidest idea. I don't. All right, I gotta pee. I'll be right back. Alright, I'm back. Should drink some more water, but then I'd have to pee again. Okay, so he's going to explain what he means by simplifying. I don't like this block matrix idea, but maybe a way to think about... Am I recording with the correct microphone? Let's make sure I'm recording. Yes, I am. Alright, I'm not a huge fan of this block matrix idea, but maybe think about the vertical bar as two sides of an equality, and you're doing the same things to two sides of an equation. So here's the way that row reduction is used to solve systems of linear equations. Suppose we are given a system of m equations and n unknowns, say Ax equals b, where A is an m by n matrix and b is a given column vector and x is an unknown column vector. Ooh! To solve this system, we form the m times n plus 1... m times n plus 1 block matrix, sometimes called the augmented matrix. M equals a bar b equals that. And we perform row operations to simplify m. Note that e times m... Like, why do you do this? Like, what... It doesn't... You're doing the same thing to both sides of an equation. That's the way to think about this. So let... Go away. Let m prime equals a prime bar... That's so stupid. Be the result of a sequence of row operations. Doing the same thing to both sides of an equality. The key observation is this. Proposition 1.2.10, the systems a prime x equals b and ax equals b have the same solutions. It's such an opaque way of stating... Alright, let's look at the quote proof, unquote. Since m prime is obtained by a sequence of elementary row operations, there are elementary matrices E1 up to EK such that with P equals EK down to E1, m prime equals EK down to E1, m equals PM. The matrix P is invertible. Right, each elementary matrix is invertible, so the product of elementary matrices is invertible, so you have EK down to E1. Well, you multiply this by E1 inverse, E2 inverse, up to EK inverse. And you do this product and you'll see that, well, the E1 cancels the E1, the E2 cancels with the E2 inverse, the EK cancels the E2 inverse, and you end up with the identity matrix. So a product of elementary matrices is always invertible. And in fact, any invertible matrix is a product of elementary matrices, which is kind of interesting. So there's like some building blocks here. Anyway, let's let Artin talk. The matrix P is invertible and m prime equals a prime b prime equals pa pb. If x is a solution of the original equation ax equals b, we multiply p on the left, pax equals pb, which is to say a prime x equals b prime. So x also solves the new equation. Conversely, if a prime x equals b prime, then p inverse ax equals p inverse b. That is ax equals b. Okay, so If you have a solution to the old equation, you also have a solution to the new equation. If you have a solution to the new equation, you also have a solution to the old equation. All right. For instance, consider the system x1 plus x2 plus 2x3 plus x4 equals 5. x1 plus x2 plus 2x3 plus 6x4 equals 10. x1 plus 2x2 plus 5x3 plus 2x4 equals 7. Its augmented matrix is the matrix whose row reduction... okay, so way up here, where's my pointer? This system of linear equations is the matrix. That matrix is the matrix of this system of linear. Where is my pointer? Here we are. Of this system of linear equations. Okay, so 1, 1, 2, 1. 1, 1, 2, 6. 1, 2, 5, 2. And then I guess it's augmented, so 5, 10, 7. That's the matrix above. I don't like this augmented nonsense. Anyway, you do the row reduction and you get x1 minus x3 equals 3. So x2 plus 3x3 equals 1 and x4 is equal to 1. So you know x4 right away. There is no freedom whatsoever in choosing x4. But if you choose x3, well, what x1 such that when you subtract x3 from it, you get 3? Well, obviously x1 is equal to 3 minus 3 plus x3. So it doesn't matter what you choose for x3. x1 is equal to 3 times x3. So if you choose, in particular, I'm going to use the eraser. If you choose c for x3, then x1 is equal to 3 times c. Well, if you choose c for x3, then x2 is equal, so x2 plus 3 times c is equal to 1. So x2 better be equal to 1 minus 3 times c. Correct? Yeah, so he actually got the same equation. So x1 equals 3 times c. x2 equals 1 minus 3 times c. x4 equals 1. We have no choice there. And x3 is equal to c. Okay, so we can read out the solutions of this system easily if we choose x3 equals c arbitrarily. We can solve for x1, x2, and x4. The general solution of 1.2.11, which is this, can be written in the form, right, exactly what I said. x3 equals c, x1 equals 3 plus 3, x2 equals 1 minus 3c, and x4 equals 1, where c is arbitrary. Now we go back to the row reduction of an arbitrary matrix. It is not hard to see that by a sequence of row operations, any matrix M can be reduced to what is called a row echelon matrix. Okay, reduced to row echelon form, that's what I was talking about earlier. The end result of our reduction of 1.2.8, which is 1.2.8, let's look. 1.2.8, okay, so it's the matrix of this system of linear equations. Is an example. So, a row echelon matrix. This is such an important concept. Is there a highlighter? Yes, there is. Let's see if we can highlight. Yeah, row echelon matrix. That's such an important idea. Let's switch back to the pencil. A row echelon matrix is a matrix that has these properties. If row I of M is 0, what? If row I of M, a row echelon matrix M is a matrix that has these properties. If row I of M is 0, then row J is 0 for all j greater than I. So in particular, if you have a row of zeros somewhere in the matrix, in order for it to be a reduced row echelon form, all of the subsequent rows also have to be all 0. Okay? That's what that means. If row I isn't 0, its first non-zero entry is 1. Okay. This entry is called a pivot. If row I plus 1 isn't 0, okay. then the pivot in row I plus 1 is to the right of the pivot in row I. Okay. So that's saying that if you have like a 1 here, and you go to the next row, the pivot better be like down and to the right. And so the pivots go down and to the right. The entries above a pivot are 0, so you eliminate everything above a pivot. Entries below a pivot are 0, 2 by part C. Right. So by part C, the pivot is the first non-zero entry, and so you should eliminate below. And so the entries below a pivot are 0, 2 by part C. Okay. The entries, the pivots in the matrix M prime of 1.2.8 and the examples below are shown in boldface. To make a row reduction, find the first column that contains a non-zero entry, say M. If there is none, then M is 0. It's itself a row echelon matrix. Interchange rows using an elementary operation. I gotta actually read this, unfortunately. To make a row reduction, find the first column that contains a non-zero entry, say M. If there is none, then M is 0 and is itself a row echelon matrix. Right, so the 0 matrix is trivially a row echelon matrix. Interchange rows, so you want to take the first pivot, put it on the top row. Second pivot should be on the second row. Third pivot should be on the third row. And that's how you get this idea that this is how you get this first property that all the non-pivot, all the rows that don't contain a pivot should be at the bottom, and the pivots should be in sequential order, kind of going down. Maybe they can skip a couple, but the pivots should kind of have this shape like this, and then all the subsequent rows down here should all be zeros. To make a row reduction, find the first column that contains a non-zero entry, say M. If there is none, then M is 0. So you're allowed to have columns that are all zeros here. So if you have a bunch of columns that are all zeros, you kind of just skip those. Find the first column that contains a non-zero entry, say M. If there is none, then M. Okay, yeah. Interchange rows, right, so you take the first pivot, move it to the top row, using an elementary operation of type 2 to move M to the top. So do a transposition, get the first pivot to the top row. Normalize M to 1 using an operation of type 3. So if the pivot is 7, multiply by 1/7. Multiply that row by 1/7, and there's a matrix that multiplies a specific row by a constant. This entry becomes a pivot. Clear out the entries below the pivot by a sequence of operations of type 1. So do elimination below. The matrix will leave the block form. Right. So you have a bunch of zeros over here which you don't care about. You have a 1 down here, and you've eliminated everything below it. Okay, and you don't care what's over here. Okay, which we will write as 0. These are all supposed to be 0. You have something here called B1, which you don't care about, something called D1. Now, by recursion, you just simplify D1. Okay. By induction on the number of rows, we may assume that D1 can be reduced to a row echelon matrix, say to D2. Okay, so the next one, M2, so this is here, this is M1, and down here is M2, this is D1 right here, and this is D2. And so D2 is now in reduced row echelon form. Okay. This matrix satisfies the first 3 requirements for a row echelon matrix. The entries in B1 above the pivots of D2 can be cleared out at this time. So we eliminate everything, we do downward elimination. And so we have something that's kind of an upper triangular-ish matrix. And then, okay, well now we have all these ones kind of on the not quite the diagonal. Okay, and then there might be stuff that isn't 0 above them. Well, we can use more row operations to eliminate those. The entries in B1 above the pivots in D2. Right, so we eliminate above in B1 to make B1 into a bunch of zeros. Or, not quite. Anyway, to finish the reduction to row echelon form. It can be shown that the row echelon matrix obtained from a matrix M by row reduction doesn't depend on the particular sequence of operations used in the reduction. Okay. Yeah, okay, so the row-reduced echelon form. There's only one row-reduced echelon form of a matrix. By the way, if a matrix is invertible, then its row-reduced echelon form is the identity matrix. And there's only one row-reduced echelon form of a given matrix. And it doesn't actually matter how you get there. The row-reduced echelon form is the row-reduced echelon form. And a matrix is invertible precisely when its row-reduced echelon form is the identity matrix. In particular, that means only square matrices can be invertible. That's important. Since this point will not be important for us, we omit the proof. As we said before, row reduction is useful because it's useful because it's the most fundamental operation in linear algebra. It's not useful for one reason, it's useful for 1,000 reasons. As we said before, row reduction is useful because one can solve a system of linear equations a prime x equals b prime easily when a prime is in row-reduced echelon form. Another example, suppose that a prime affix... Oh, this block matrix is so stupid. What? Oh, this... Okay, Artin, I should acknowledge, and I should be humble. Artin knows way more about algebra than I do. So that's a thought. But anyway, there's no solution. Right, so another example, suppose that a prime b prime equals 16011, a00123, 00001. There is no solution to a prime x equals b because the third equation is 0 equals 1. So you multiply... Right, so 16010012000 times x1, x2, x3, x4. And the bottom row of this will be 0x1 plus 0x2 plus 0x3 plus 0x4. That's obviously going to be equal to 0, but the bottom equation says it has to be equal to 1, so there's no solution. That's just a contradiction. Suppose there is a solution, we can prove that 0 is equal to 1, which is a contradiction. That's the proof. On the other hand, right, so if you have a 0 here, this has solutions. Okay, so if x4 is equal to c, this has solution. So if x4, let me just try to solve this myself. If x4 is equal to c, then x3 plus 2c is equal to 3. X3 is equal to 3 minus 2c, then x1 plus 6x2, right, plus x plus c is equal to 1. X1 plus 6x2 is equal to 1 minus c, and this is going to give you like this is going to give you a line of solutions in the plane. Right, this is just a linear equation. So this is describing the equation of a line because c is fixed. It says any point on that line will be a solution. Okay. Correct, okay. But there's 2 degrees of freedom. Anyway, the general rule is this, proposition 1.2.13, let m prime equals a prime b prime be a block row echelon matrix where b prime is a column vector. The system of equations a prime x equals b has a solution. Need some more water. If and only if there is no pivot in the last column b prime. Right, so... Right, okay. Because if there was a pivot in the last column b prime, we can look at this equation, then everything before it would be equal to 0, and then we have 0 equals 1. Right, okay. In that case, arbitrary values can be assigned to the unknown x sub I. Sorry, I got what is it? Acid reflux, provided that column I does not contain a pivot. So the columns that don't contain a pivot, those from this kind of past pattern of argumentation, correspond to degrees of freedom. So arbitrary values, that means there is a degree of freedom, can be assigned to the unknown x sub I, provided that column sub I does not contain a pivot. So the columns that don't contain pivots, there's a degree of freedom there. When these arbitrary values are assigned, so once you eliminate all the degrees of freedom, there's no more degrees of freedom left, and everything is determined. The other unknowns are determined uniquely. This white square, by the way, means QED, which means that the proof is over and I'm done. Every homogeneous linear equation AX equals 0 has the trivial solution x equals 0, but looking at the row-reduced echelon form again, we conclude that if there are more unknowns than equations, so if it's a fat matrix, so if it's a wide matrix, so if there are more unknowns than equations, correct, okay, because then the pivots, you'll run out of pivots. Then the homogeneous equation AX equals 0 has a non-trivial solution. Because you can, if you have degrees of freedom, you can kind of choose things to cancel out. Okay. Corollary 1.2.14. Every system AX equals 0 of m homogeneous equations and n unknowns, with m smaller than n, so there are more unknowns than equations, has a solution x in which some x sub I is non-zero. So what this means is that you have more degrees of freedom than there are dimensions. And so you can choose your degrees of, the values of your degrees of freedom so that they cancel out. Okay, let's look at his proof. Row reduction of the block matrix A bar 0 yields a matrix A prime bar 0. Right, because all of the row operations, when you apply them to 0, an easy way to see this is, where is it? E of 0, 0, 0. Well, any matrix times 0 is just going to be equal to 0, 0. That's supposed to be 0, 0. Right, any matrix times the 0 vector is equal to the 0 vector. So you do these row operations on this, and you're still going to end up with the 0 vector. It's only going to operate on A prime, in which A prime is in row echelon form. The equation A prime x equals 0 has the same solutions as AX equals 0. The numbers say R of pivots in A prime. Okay, let's read that again. The equation A prime x equals 0 has the same solutions as AX equals 0. Correct. The numbers say R of pivots in A prime is at most equal to the number m of rows. So it is less than n. The proposition tells us that we may assign arbitrary values to n minus r variables x sub I. I need some more water. Let me think about what this says. So there's not going to be any pivots in the column because all of those are equal to 0. Okay. Or on the right end of the juxtaposition. So there's never going to be any pivots in this A bar 0. There's never going to be any pivots in the 0 vector, in the 0 column. Okay. The number of pivots in A, right, so you can't have, there's one at most one pivot per row. There's more columns than rows. And so, obviously, there are going to be fewer pivots than there are columns because there are more columns than rows, and at most one pivot per row. Okay. And the proposition says, what proposition? Right, proposition 1.2.13. So, yeah, okay. Then you have n minus r, so if r is the number of pivots, then the number of columns minus the number of pivots, that's how many degrees of freedom you have left. And you that means you may assign arbitrary values so that you have that many degrees of freedom. And then once you have fulfilled all of those degrees of freedom, no more degrees of freedom left. Okay, yeah. We now use row reduction to characterize invertible matrices. Lemma 1.2.15, a square row echelon matrix M is either the identity matrix I or else its bottom row is 0. Think about that. Right, so this is what I was saying earlier. Huh? Let me think. A square row echelon matrix M is either the identity matrix I or else its bottom row is 0. Okay. Let's look at his proof. Say M is an n by n row echelon matrix. Since there are n columns, there are at most n pivots, and if there are n of them, there has to be one in each column, and in which case you will eliminate above and below. And then in that case, M is equal to the identity. Okay. If there are fewer than n pivots, then some row is 0, or else its bottom row is 0. That's important. Where is my pointer? Bottom row. Then the bottom, right, so then at some point you'll run out of pivots and you'll have a row of zeros, after which every other subsequent row must also be 0. Alright. Theorem 1.2.16. Let A be a square matrix. The following conditions are equivalent. A can be reduced to the identity by a sequence of elementary... Right, so this is what I was saying earlier, that a matrix is invertible precisely when its row-reduced echelon form is the identity matrix. He has described the procedure for going from a matrix to its row-reduced echelon form. In particular, here's the basic idea. So you have some matrix A, and it's invertible. You multiply it, you keep doing elementary operations, down to E sub k, and then this is equal to the identity matrix. So this is invertible. Well, then E sub k down to E1, this is equal to A inverse. Wow, that's a terrible -1, but you get what I'm saying. Well, then you take the inverse of this, so E1 inverse up to EK inverse. Well, that better be equal to A. Well, the inverse of each elementary matrix is an elementary matrix. So now A is written as a product of elementary matrices. Right? So these two... Right, so this B clearly implies C because if you write A like this, you just take the inverse. There's its inverse. It's a bunch of elementary row operations. And then, right, so we've proved just from this little argument that A and B are equivalent. Okay. Well, if A can be reduced to a sequence, then clearly A is equal to C. Or A implies C. Okay. If A is a product of elementary matrices, clearly B implies C. And then, so following conditions are equivalent. So he proves A implies B implies C implies A. And that's kind of cute. And the way he proves it, I don't care for the way that he proves that C implies A. He proves the contrapositive, which is that not A implies not C. But let's just read his proof. We prove the theorem by proving the implications A implies B implies C implies A. Suppose that A can be reduced to the identity by row operations, say E sub k down to E sub 1 A equals I. Multiplying both sides of this equation on the left by E1 inverse up to EK inverse, we obtain A equals, so exactly what I wrote. Exactly what I wrote. These two. Exactly the same. A equals E1 inverse up to EK inverse, since the inverse of an elementary matrix is elementary, B holds, and therefore A implies B. Okay, because a product of invertible matrices is invertible, correct, so B implies C. Finally, we prove the implication C implies A. If A is invertible, so is the end result of its row reduction. Since an invertible matrix cannot have a row of zeros, right, if you have a row of zeros, then that row will always go to 0. So if you have a row of zeros in a matrix, where is my pointer? 0, 0, 0, 0. By a previous argument, you multiply this by a column vector. Let's just call this x. This will always go to 0. Or to the 0, yeah, this is the 0 scalar. Then if you put something that isn't 0 here, there's no solution, so it can't be invertible. Since an invertible matrix cannot have a row of zeros, lemma 1.2.15, which I assume is a square. Yeah, okay. Yeah. Shows that A prime is the identity. QED. Okay, phew. I feel like we should take a break. Let me have some more water. Let me read this next paragraph silently while I drink my water. Right, okay, so this is kind of a weird way to make this point. Row reduction provides a method to compute the inverse of an invertible matrix A. So we reduce A to the identity by row operations. EK down to E1A equals I as above. Multiply on the right by A inverse, so then you would have EK down to E1 equals A inverse, which is what I said before. Right. There. Let A be an invertible matrix. To compute its inverse, one may apply elementary row operations E1 up to EK to A, reducing it to the identity matrix. The same sequence of operations when applied to the identity matrix I yields A inverse. Duh! That's obvious. So A be an invertible matrix. Right. So this is all this corollary is this equation. That's this corollary, but instead of this obvious equation, you put it in this 3-sentence long paragraph and then put the white square here to make yourself feel special. How much longer do we have? Alright, we'll only have like a page and a half left. Let's just power through this. Example 1.2.18. We invert the matrix A equals 1526. To do this, we form the 2x4. This block matrix thing is so stupid. To do this, we form the 2x4 block matrix. A bar I equals 15261011. We perform row operations to reduce A to the identity, carrying the right side along, and you'll end up with the inverse on the right because this block... I don't like magic. I like when things are transparent, and this block matrix thing is magic, and I don't like that. But yeah, you do row operations to A, and you do the same operations to the identity. So you do the EK down to E1 of A. Well, you do the same thing, EK down to E1 of the identity, and then this is going to be A inverse. This is going to be the identity. And that's all this is. But it's doing in this tabular form, and tables are stupid. Proposition 1.2.20, let A be a square matrix. Let me make sure I'm recording. Yes. Let A be a square matrix that has either a left inverse or a right inverse. A matrix... That's the definition of inverse. Why is that a proposition? This is what is annoying when going through the basics of mathematics, is the definitions and theorems. There's The theorems are so obvious, they're just almost the same as the definitions. Let's continue reading. 1 second. Let me read this silently. That's a definition of inverse. I have to pee again. Let me go pee, and then we can read this again. Okay, this is the definition of inverse. I don't know why this is a proposition. Anyway, suppose that A times B equals I. Oh, this is such a weird way to prove it. We perform row reduction on A, say that A prime equals P times A, where P equals E to, okay. P equals EK down to E1 is the product of the corresponding elementary matrices, and A prime is a row echelon matrix, and then A prime B equals PAB equals P, because P is invertible, the bottom row isn't 0, so then the bottom row of A prime can't be 0 either? What? Right. What? I don't understand this sentence. This is such a weird way to prove it. I don't understand this sentence, but let's just move on. I'm tired. Therefore, A prime is the identity matrix. Because it's in row reduced echelon form. Okay. So P is a left inverse of A. Then A has both a left inverse and a right inverse, so it is invertible, and B is... That's so weird. If BA equals I, we interchange the roles of A and B in the above reasoning. We find that B is invertible and its inverse is A. Okay. It's a definition of its definition. Okay. Square systems. Okay, the following conditions on a square matrix A are equivalent. A is invertible. The system of equations AX equals B has a unique solution for every column vector B. The system of homogeneous equations AX equals 0 has only the trivial solution x equals 0. Proof: given the system AX equals B, we reduce the augmented matrix A bar B to the row reduced echelon form A prime bar B prime. The system A prime x equals B has the same solutions. If A is invertible, then A prime is the identity matrix. So the unique solution is x equals B prime. Yes, okay. This shows that A implies B. So if A is invertible, we can reduce it down to here is x, here is B prime. So if A is invertible, so we have AX equals B, then that is x equals A inverse B. Well, this is going to be a column vector, so there. And it's a unique solution. That shows that A implies B. Okay. if an n by n matrix A is not invertible, then A prime has a row of zeros. Okay. One of the equations making up the system A prime x equals 0 is the trivial equation, so there are fewer of n pivots. Okay. Right. Okay. The homogeneous system A prime. So he's proving the contrapositive. The homogeneous system A prime x equals 0 has a non-trivial solution 1.2.13, and so does Ax equals 0. This shows that if A fails, then C also fails, hence C implies A. So if A is not invertible, then there's a non-trivial solution to Ax equals 0. And of course, C is a special case of B. You replace B with the 0 vector and you get C. So B implies C. So he's proving a cycle of implication. So A implies B implies C implies A, so therefore they're all equivalent. We want to take particular note of the implication C implies B of the theorem. If the homogeneous equation Ax equals 0 has only the trivial solution, then the general solution Ax equals B has a unique solution. That is interesting. This is useful because if the homogeneous equation Ax equals 0 has only the trivial solution, then the general equation Ax equals B has a unique solution for every column vector B. This can be useful because the homogeneous system may be easier to handle than the general system. That is interesting. Okay. If you know some linear algebra, that's just obvious. Example 1.2.22, there exists a polynomial P of t of degree n that takes prescribed values, say P of ai equals bi at n plus 1 distinct points. Where is this? Okay. N plus 1 distinct points on the real line. Okay. To find this polynomial, one must solve a system of linear equations in the undetermined coefficients of P of t. In order to not overload the notation, we'll do the case n equals 2 so that P of t equals x naught plus x1t plus x2t squared. Let A0, A1, A2 and B0, B1, B2 be given. The equations to be solved are obtained by substituting ai for t. Moving the coefficients x sub I to the right, they are x0 plus ai x1, okay, plus ai squared x2 equals bi, for I equals 0, 1, 2. This is a system ax equals b of three linear equations and the three unknowns, x0, x1, x2 with, okay, right, this is the same, this equation generalized over I is this matrix, and times, let me write this, x1, x2 equals 0, b, this is a 0, b1, b2. That's what this is. The homogeneous equation in which b equals 0 asks for a polynomial with three roots, a0, a1, a2. A non-zero polynomial of degree 2 can have at most two roots, so the homogeneous equation has only the trivial solution. Therefore, there is a unique solution for every set of prescribed values b0, b1, b2. By the way, there is a formula, the Lagrange interpolation formula, that exhibits the polynomial p of t explicitly. Okay. That's kind of interesting. Alright, but we're done. Finally. Alright. Thank you for watching, if you watched all the way to the end. Please join me next time. I guess we're going to read the matrix transpose. Oh my god. Anyway, that was 17... 14, 13, 12, 11, 10. So that was like 8 pages, and it took us probably over an hour. I'm not entirely sure about the time. But that's, math just takes a long time to read, and it's kind of frustrating. You say, oh, a 600-page book, I can read that in a few days. And it's like, no, you can't. That's going to take you a year. And it's just, the information is so dense. It's very dense. Anyway, thank you for watching. That's all. Please join me next time. I'm Dr. AJ Kumar, PhD.